everyone, Mr. Lee here. In this video, I'm going to go over the kinematics unit. Now, I'm doing it a little bit more freeform, so I'm just putting down the ideas and the thoughts as they really come to me. Okay, so you should have these down in your notes from before, but here's just a couple of highlights. So if you remember from the kinematics unit, we have a couple of definitions. The first one is velocity. Okay, so velocity, well, the equation is the displacement over the change in time. So this is a lot like speed, but speed is distance over time. So a couple things you need to know about velocity. The first thing is that velocity is a vector. So direction matters. Okay, direction matters. So if you say something has a velocity of -5 meters per second, so I'm going to highlight this right here because this is one of those warnings. Right? A lot of students think that if you have a negative velocity, the object is moving slow or it's slowing down, but that is not the case. It just simply means that it's moving in the negative direction. Right? So that's a big one. Also, it's over a period of time. Okay, so this meters per second is showing you that it is the displacement over seconds is a unit for the change in time. Okay, all right. That leads us to acceleration. Now, acceleration, we had the equation to be the change in velocity over the change in time. Now, acceleration is the change in velocity, so we can either speed up, we can either slow down, or we can change our direction. So if you're like in a car has three things that have acceleration things linked to it, such as the gas pedal helps you speed up, the brakes help you slow down, and the steering wheel helps you change direction. So those three things help your car accelerate. Okay, so if it's a change in velocity over a change in time, we had the units of meters per second over second, which gives us meters per second squared. All right, so that's our units. Now, I'm going to highlight a couple of things. The first one is how to read a velocity acceleration, like if you're given like a table or like if you're given a graph. So let's start off with that. First off, if your velocity and your acceleration have the same direction, positive velocity, positive acceleration, that means you are speeding up. If you have different values, then that means it is slowing down. Okay, notice how I phrase that. If you have negative acceleration, that does not mean that your object is slowing down. The object is slowing down only if your velocity and your acceleration are different. So what this shows us is, well, now we can link the forces unit because we just covered that, but we know that Newton's second law states that we have F equals ma, so that's a force, right? So a force is either a push or a pull. So if there's a force, an outside net force acting on an object, the object will accelerate. That's the definition of a outside net force. And so if you have an object moving towards the right, and the object is accelerating to the right, so that means, according to Newton's second law, that there was this outside net force that caused this object to accelerate to the right. So we have an object that's moving to the right, and some force pushed it to the right. That's what this actually means here. So that means that the object will be speeding up. Okay. Now in the opposite direction, or the flip-flop, right? We have a object moving to the right, but there's a push. There's a push in the negative direction, so that will be slowing down. So in terms of the car, right, we can think about this as like the gas pedal. Okay, the gas pedal will help you speed up, and this like the brakes. The brakes will slow us down. And I want to emphasize one more time that negative does not mean slowing down, because if I were to create a straight line, there we go. If I were to look at the other side, we would say that a negative velocity with a negative acceleration means that the object is speeding up. Okay, so if I'm going back to the car analogy, this negative acceleration will be the gas pedal, and we know that because the object is speeding up. So this just means that you're moving towards the left, right? And something is pushing you towards the left. You're going to speed up. And on the reverse, if we have negative velocity but with a positive acceleration, that means that you are slowing down. Okay? Now, I'm going to add one more to this. If you have a velocity of 0, that means you are not moving, but you experience either a positive or a negative acceleration, you will speed up. Okay? And that should make sense. So like if we have an object just sitting there, remember, an object at rest stays at rest unless there is a outside net force. And once again, if we take a look at the net force equation over here, if we have an outside net force, that must mean that the object M will accelerate A. So if we just have an object sitting there and there's a reason for that object to accelerate, the object will speed up. Okay? Very important table because that's going to help us when we take a look at graphs. So we have three kinds of graphs that we can look at. The first one I want to focus on is the velocity time graphs. So if I have a velocity time graph, like so, okay, and I'm going to have this line be blue. Okay, so if I have a velocity time graph and we have an object going like this. So these are the couple of things that we can tell. First, the velocity is positive. Okay. The second thing that you need to know is that for a velocity time graph, the slope is the acceleration. And this is how we know. Slope, let me put this off on the slide. Slope is a division. Okay, slope is a rise over run. So if it's a rise over run, we have velocity over time. And this matches up with our acceleration equation, velocity over time. Okay, rise over run. Our rise is our velocity, our run is our time. Another way that you can do this is if we have our units here, meters per second, and our time units are seconds, the units for velocity is meters per second, and the units for time is seconds. So when we simplify this, we get the units of meters per second squared. Okay, so this right here, this is our rise, and this right here is our run. Okay, rise over run, meters per second squared. So the units for rise over run gives us the units for acceleration. All right, so if I take a look here, the slope is a positive slope. So we have positive velocity because it's above the x-axis, like the data points are, and we have a positive acceleration. So that must mean that this object is speeding up. And we know this. We can gather evidence for this because if we focus right here at the starting point, okay, right there, the object started from rest. That's a velocity of 0. That means the object is not moving at all. And if the object is not moving, but after a certain period of time, we'll call this TF for T final, after a certain period of time, the object is moving with a certain amount of velocity, that means that it's sped up, right? So we start off with no velocity, but we end up with some velocity, it's sped up, okay? So another way that we can look at this, I'll create another graph down here. We're going to be doing a lot of graphs today, okay? A lot of graphs. So if we have something that looks like this, let me do this in a different color. There we go. All right, what can we tell? So I want to break this up into two parts. Part one, we're right here. So in this part, we know that the velocity is positive. Sorry, I wrote a T there instead. So we have a positive velocity, but look at the slope. This slope is pointing, well, it's going down. And we know that the slope for a velocity time graph represents our acceleration. So we have a negative acceleration. And this should make sense because if we focus right here on that part right there, okay, that's when your velocity is 0. That's when the object comes to rest. Okay, so when we describe objects, motion, the motion of an object being at rest is so very important. It tells us so much. So this tells us that the object had an initial velocity. It was moving. Okay, it was moving in the positive direction. But for whatever reason, there was an outside net force that caused this object to slow down eventually until the object came to rest. That's what this graph is telling us. So this object slowed down. And we know this for sure because if we take a look here, the signs are not the same. They're different. All right, so if we take a look down here in part 2, we see that down here the velocity is negative because we are below the x-axis, and our slope is still negative. Look at that, the same signs. Therefore, the object sped up. Okay, and we know this because the object here had a velocity of 0, and eventually it had a velocity of, I don't know, some negative value right here. Right, so we'll call that VI of negative velocity. We don't know what that is, but it's moving. Now, pitfall. Students, I keep on saying this, students want to think that if an object has a negative velocity, it is moving slowly, it is slowing down, or any of the iteration of the two. Okay, it is a slowly moving object that is slowing down. That's not the case. Okay, that is not correct. A negative velocity simply means that the object is moving towards the negative direction. Okay, it has a speed, but the direction is negative, right? So let's try one more. So if we have a velocity time graph here, okay, and let's do a straight line right there. Okay, so here if we take a look at this, assuming that this is a straight line and this is our initial velocity, and right here will also be our final velocity. Let me rewrite that, excuse me. We can say that our initial velocity right there is equal to our final velocity, which is over here, right? Same values. What this tells us is that the object has zero acceleration. So let's take a look at this, right? We know that the velocity is positive, but what about our slope? What is our slope? Good, there is no slope because there is no rise, right? Our rise is 0. So if you have no change in velocity, remember that is a definition of acceleration. That's a change in velocity. If you have no change in velocity, that means the object is neither speeding up, slowing down, or changing directions. Okay, there is no change, delta, in velocity. Okay, so now I'm going to work backwards here. The other thing that you need to know how to do is how to take a look at a graph's area under the curve. So if I focus on this graph over here, I'm going to just label it as AUC, area under the curve. Area under the curve is the multiplication. Okay, the multiplication. You're going to multiply. And so what that means is it's a base times height area, right? Base times height is the formula for area. And our base units, or our base is time, that's the variable, and our height, the variable is velocity. Velocity times time. That gives us displacement. Okay, and we know this because over here we have velocity is displacement over time. Okay, in order for it to look like this, I'm going to multiply both sides by the time on both sides to get time times velocity. This cancels out, is equal to displacement. All right, it just falls right in place with our equation. Now, just in case you forget that equation and you're like, I need to figure out what the area on the curve represents, this is how you do it. Our units for time is seconds. Our units for velocity is meters per second. And when we multiply the two, the seconds, I'm going to get my red pen over here, the seconds, it cancels out, leaving us with just the meters variable, and the units for displacement is meters. All right, so in order to figure out the actual displacement here, we need to find the area. So the area right there is the displacement traveled by this object. Okay, so in terms of the AP questions, if you see a velocity time graph, three things technically should immediately pop into your brain. One, what are my velocity values, right? Do we have any zeros anywhere? What is our initial velocity? Is our initial velocity positive or negative? Next thing, think about what is the slope? Slope is the acceleration. What is the area under the curve? Area under the curve is displacement. These three things should be firing in your brain as you read the question. So when you're reading the question, if it comes across like the question is asking about displacement, boom, ignore the slope, go straight into area under the curve. Okay, view that question through the lens of area under the curve. And then look at the answer choices, okay? Solve it in that fashion. If you're looking at the question and it's talking about acceleration and they're giving velocity time graphs, boom, focus your mind on the slope. Find the slope and see where that gets you. Okay, so that's a little sidebar, but if we take a look up over here, I want to show you something with the area under the curve. I'm going to do this in two different colors. The first one I'll do orange. So we know that the area under the curve here, so this shape is a triangle. So this is my area right there. Okay, and that is the displacement for the first part of the trip. And this displacement, we will find it by 1/2 base times height. So velocity versus time, right there. That is our area for the first part of the trip. And the second part of the trip, so this is where a lot of students get confused. The area under the curve is always from the curve, okay, the line, so a line is a curve, to the zero. So I'm going to do this in a different color. Let's do this in green. So this is my line, this is my curve, and this is the zero, the horizontal. So right here, the part that I shaded in, that is the area under the curve. Okay, that tells us the area under the curve. And you got to be careful. Right here, this is I'm going to make this nice and bold. This is a positive displacement. And right here, this is a big fat negative displacement. Let me write that in instead. of doing this shading. All right, so this is a positive displacement, and here we have a negative displacement. And it's negative because if we're doing base times height, our height is a negative value. Okay, so be very careful. That is one way that the AP questions, they can get you. Now, if they're asking you for the total displacement from your initial time to your final time, okay, your total displacement, you're going to be adding whatever displacement is here in the first part, and you're adding it to whatever displacement you find here in the second part. Okay, now listen to how I stated my words. You are adding it. So if this is a negative displacement, okay, you're adding it to the total. So all in all, you're subtracting according to the laws of math, right? So in like a real life scenario, what are we looking at here? So we're looking at an object that's moving, let's say positive is forward, right? Where we have an object, let's say we have a car, and this car is moving forward. It's moving forward, but what we know is happening is that this object is slowing down. So it moves forward, and it slows down, and it comes to a stop. Okay, it comes to a stop. And then the second part of the trip, it's moving backwards. This is our negative velocity. So the second part of the trip is moving back. Okay, and if this area in part 1 matches the area in part 2, our displacement would be 0. So that just means that you started and you ended in the same location. Okay, all right. So same thing over here, area under the curve, you're just taking a look at the area under this part right here, and you're going to be finding that area. All right. Now, let's say, well, I'll do a different graph. We get something that looks like this, right? We have a velocity time graph, and I'll do this in blue. We get something that looks like this. All right. Boom. Okay, so that's our velocity time graph. And for, you know, your brain, you're like, I don't even know what to call that shape, let alone find the area of it. Here to help you. We can break this shape up into two parts. The first part will be down here. I will shade this in orange. So this is part 1. Right there, part 1. This right here is our rectangle. And the area for a rectangle is just simply base times height. Okay? Now, up above, I'm going to do this in green, right here, part 2. That area is our triangle, which is 1/2 base times height. Now, here's the pitfalls of this. Remember, the height of this triangle starts from here, ends there. What a lot of students want to do is they want to go from the 0 all the way to the top, but that's not the actual height of the triangle. The height of the triangle starts from this point down here, and it ends up right there. Okay, and then after you find the two areas, okay, 1/2 base times height plus base times height, you would just add them together to find the total displacement, right? So if I were to fill in the variables here, so our height is velocity, and our base is time plus base is velocity times time equals change in. Okay, so we get something that looks like this. Now this equation should look familiar. This equation should look very familiar. So that leads us to our kinematic equations, because that equation leads us to our kinematic equations. But before we do that, let's do the other two graphs. Next graph. So the next graph that I want us to focus on is the position versus time. Okay, the position versus time. So if I have a position versus time graph, and there's a couple of things that you can look at. Remember, 1, always look at the points. And 2, you're going to look at the slope. Now, if you remember, slope is the division. Okay, slope is division. Because we have rise over run. That over signifies that it's division. So let's do our units trick. The units for position is meters. The units for time is seconds, meters per second. We could also do this with the variables. Our units for rise is the change in position, because that's a difference, and change of time. Hey, that looks familiar, right? Meters per second, or displacement over time. That gives us to velocity. So the slope for a position versus time is velocity. All right, So we have slope to be velocity. So if I want to show you the different kinds of slopes that you might see. And we did some practice with this, but it's just a good reminder. Okay, so the first one I'll do in blue. Right? So this tells us that we have a positive slope. So for this one, we have a positive velocity. Okay, and it's constant, assuming that's a straight line, right? So it's not speeding up, it's not slowing down. It's a constant slope, constant velocity, no acceleration. I'll write that. Your acceleration is 0. Why? Because this is a straight line. All right. Next one that we can do, I'll do this in a different color. I'll do it down here. Look at that. Okay, what's our slope? Our slope is 0. So our velocity is 0. Okay, because there's no slope. Okay, there's no slope, there's no velocity, the object is staying still. So at the beginning of your time interval, right here, okay, time is 0 when you start timing versus when you end, right there, you did not change your position. Your position stayed the same. Okay, and let's see. If I were to do, these are the fun ones, right, the curved ones. So let's take a look at the curved position versus time graphs. So the first one I'm going to do, let's do it in blue. Let's take a look at this. Yeah, look at that. Okay, so how, like, we have a curved line, and we can't find the slope right now with just that curved line, right? Later on, if you take like advanced math such as like calculus, you'll be able to find the slope of that line. But like, we don't have to worry about that. We just got to look at it, and we have to understand what's going on. So what I like to do is I like to take a look at it in parts. The first part right here, look at that. The slope is pretty flat, right? So if we have a flat slope, we can say that the velocity is 0. Okay, it starts off with 0 velocity, and towards the end, look at what happened there. Okay, towards the end, this is a pretty vertical line. That means that, you know, we have a slope, and in this case, the slope is going to be positive because it's going upwards. So we have an object that started off with a velocity of 0, and it led to some positive velocity. So that must mean that this object accelerated with a positive value because it sped up. Okay, it went from not moving to moving, so that must mean that it sped up. Okay, we know that it ends up with a positive slope, positive velocity, therefore the acceleration has to be positive. Okay, so it's kind of like a logic thing. All right, now let's compare that to, if I were to erase there, I'll just create a new graph. All right, so we have a position versus time graph, right? And I'll do this in blue as well. We start off with, let's see, something that looks like this. Okay, I'm just going through the x-axis just to show you that that's possible, and we're not really focused about that. Okay, so initially, if we take a look right there, initially, that velocity, it's pretty steep, right? There is definitely a slope, and that gives us a negative velocity. Towards the end, we notice that it kind of flattens out. So it goes from a negative velocity towards a velocity of 0. So we are coming to rest. That must mean that this object is slowing down. All right, so let's think about this. If we start off with a negative velocity and we are slowing down according to our chart, that must mean that our acceleration is positive. We have a positive acceleration. And we got that through the little tricks that we came up with, you know, the logic. If it slows down, that must mean that the signs are different, are opposite. Okay? All right. And we can do this with like all kinds of curved graphs, but I want to show you something else. So this is a very popular question that they love to ask. I'm going to have 2 lines. The first one I'll do blue, and the second one I'll do in green. Okay, and I drew it this way on purpose. Okay, so the dotted line and the solid line. So I will call this object 2, and the other one I will call object 1. So a question that they could ask is, let's say right here at this time interval, right there, what's going on? Okay, And that part right there is when the two lines intersect. So when I'm analyzing this, that point, okay, that point, we're not looking at slope, we're not looking at area under the curve, we're not looking at any of that. We're just looking at that point when they intersect. And when we're looking at points for position versus time graph, we are just looking at the position. So we can say that, let's say this is time 1, t1. At t1, the two objects are at the same position. Two objects at same position. Okay, they are at the same position. Now, another question that they could ask is, well, how can you describe the two objects, right? The motion. So we can say that object 1 versus object 2, right? The velocity of object 1 versus the velocity of object 2. Now we're taking a look at the slope. Okay, so the slope that we can see is that object 2, that's a pretty steep slope. It's going negative, yes, but negative does not mean slow, versus object 1, which is not as steep as object 2. So we can say that the velocity of object 1 is less than the velocity of object 2. Alrighty? Cool. So another version of that kind of question is if we're going to go back to our velocity time graphs. We can have something that looks like this, right? We have, this is, I don't know, velocity 1, and we have like an object 2, and it kind of looks like this. Something like this. Okay, so we have these two objects, and they have two different velocities. If they ask you right there at that point right there, we'll call that T1. At T1, what's going on? Okay. The only thing that we know, because we're looking at the point, okay, we're looking at the point, and for a velocity time graph, the points tell us the velocity, and the velocity values only. The only thing that we can tell is that the two objects have the same velocity. That's the only thing we know. The other thing we know, if we look beyond, is that object 2 will go faster than object 1. Okay, because the velocity values increase compared to object 1. But we don't know that. We're just looking at that point right there. Okay, they have the same velocity. So another question that they could ask is, like if this was a race and the first object started, or object 2 started off with 0 velocity and object 1 started off with, I don't know, like a velocity of v, right? At t1, who's ahead? Who's ahead? Okay, so that question is asking about the displacement. Who is ahead? So what that tells us is if we're looking at the displacement, we're looking at area under the curve. So if I were to compare the two areas under the curve, the first one, I'll do object 1. Object 1 has this area right here, that rectangle. That rectangle versus object 2's velocity, which is this triangle. So if we're taking a look at the area equation, area is base times height. Object 1 has an area of base times height, but object 2 had an area of 1/2 base times height. So we can even say that object 2 is half as far as object 1, or we could say that object 1 is 2 times as far as object 2. So watch out for that. Watch out how they word the questions. And once again, you're looking at either the points, the area in the curve, or the slope. And for a position versus time graph, you only have to worry about the slope and the position, right? Because there is no area in the curve. Okay, last one. We're going to take a look at the acceleration versus time graph. The acceleration versus time graph, we have something that looks like this. Okay, and for these kinds of graphs, they will almost 100% be flat lines, right? So here we have object 1, so we'll call that A1, and let's say this is like, I don't know, A2, and we have something like this, and we can say that this is, you know what, let's make this a little bit more extreme. There we go. We have A3. Okay, so the way that they could ask questions is if we're taking a look at A1, and the problem is like, okay, in A1 we have a negative velocity. Okay, object 1 has a negative velocity. What's happening with the object? Well, here we know that the object has a negative velocity, but the acceleration is positive. Okay? So if these two signs are opposite or different from each other, then we know that the object is slowing down. So we can say that the object is slowing down, right? Compared to like V2, let's say V2 has like a positive velocity, right? So the problem tells you that it's a positive velocity. And we take a look here and we see that A2 is also positive. We can say that the object is speeding up. And we can say that because the two signs are the same, right? And if we take a look at V3, we can say that, I don't know, let's say V3 has a negative velocity and A3 is negative, right? Because it's down here, we can say that it's speeding up. Okay, A3 is speeding up. Now, if we were to ask, okay, if the problem were to ask, if we were to compare V2 versus V3, or the object 2 versus object 3, over a long period of time, okay, over a very long period of time, and they usually write this like this, t approaches infinity, right? So these two greater than symbols means that it's like, you know, a really, really long time. Okay? As t approaches infinity, which is a really long time, which object will have the greater speed? And the way we approach this is we take a look here, right? So object 2, it doesn't have a great, like a big acceleration. It's pretty close to this 0 axis compared to object 3, which, you know, I purposely drew it way down here. So the acceleration is greater. Now remember, the definition of acceleration means that object is speeding up, slowing down, or it's changing directions. Okay? So if A3 has a greater acceleration, that must mean that it is speeding up at a greater rate. Okay? It's getting faster and faster and faster at a greater pace than A2, which doesn't have a bigger acceleration. Right? Cool. Next thing I want to go over are the kinematic equations. So I'm not going to go over how to use the kinematic equations because that's just like plug and chug, right? But I want to show you how the questions will be asked. So we have our 3 kinematic equations here. All right. So let's say that, I don't know, we have an object, and this object is we have an object here, and this object is moving along with a velocity, right? And this object falls off a cliff. There we go. All right, whee, boom. So let's say the initial velocity is v, all right? And it falls off a distance of xf. So it goes towards xf. A common type of question that they'll ask is, if we increase the velocity of the ball from v to, let's say, 3 velocity, right? It's moving 3 times that fast. How far will it go? So if we take a look at the second equation will help us determine this. So I'm going to write out the second equation over here. 1/2 at squared. Okay, so in this scenario, because we're looking at the x-axis, right? The x-axis, the acceleration is 0. That's one of those memorize ones, right? And we know that the time it takes for this object to fall, it doesn't matter if it's going 3 times as fast, as 3 times as slow, as 10 times as fast. The time it takes for an object to fall from the same height is the same. So we don't have to worry too much about the time. But what we do have to worry about is this velocity value right there. Another thing, our initial position here is 0, right? So from here to here, this right here is position 0. So what this turns out to be is xf is equal to v initial t. So this is like trial 1. Like this is when the velocity was just v. Compare that to when the velocity is 3v. When the velocity is 3 times as big, but your time doesn't change, in order for this left-hand side to match whatever we did on the right-hand side, right? According to the rules of math, whatever you do to one side, you have to do to the other. I multiply the right-hand side by 3, therefore my left-hand side also has to be multiplied by 3. So what this means is that if you're moving 3 times as fast, you will go 3 times as far. Okay, so that's one way of doing things. Another way of doing things is they love this. They love doing this. So this t squared right there, they'll say something like, Ooh, okay, so we have a object that falls, right? So we have an object and it's falling towards the ground. And we know that xf is 0 because it hits the ground, but xo is just like some height. We don't know what that height is. But they say that from this height, it falls for a total time of t. Now, they will then ask you, they will say, if we double or triple, let's do triple, right? If we triple the time it takes to fall, so I'm just going to draw this up here. I'm running out of space. So if we triple the time it takes to fall, so that's 3 times, that's 3t, how high up did we release this ball, right? What is our xo? So if we're tripling the time it takes to fall, if we take a look at this equation, we have this t squared. So all you have to do is you have to plug this 3t into a t squared to get our answer. Because we know that the final position, that doesn't change, that's the floor. Our initial velocity doesn't change, right? Because when we release an object, the object starts off with an initial velocity of 0. So all this will be 0, and the acceleration due to gravity, that won't change. So that's just a constant. So what we're looking at, right? So if I have this equation here, I'll write out all the things we can cancel again. So we have this equation. We know that the initial position, or excuse me, the final position will be 0. Cancel that. Our initial velocity is 0, so all this gets to be 0. And so we are left with an equation that looks like this. A t squared. Oh, excuse me. And the other thing that we know is that our acceleration due to gravity, that's a constant. So let's get rid of that. Okay. Also, this 1/2, that 1/2 is also a constant. That 1/2 will never change. It will always be a constant. So like in terms of the grand scheme of things, we get rid of it. And we get rid of it because it's not actually affecting this scenario, right? It doesn't help us determine the final, like the ratio. All right, so we're left with something like this. So what we have to do next is we have to get this 3t, and we have to plug it in right there for t squared. And so what that gives us is we get 9t squared. Okay, so this 9 tells us everything that we need. So remember, whatever we do here, we have to change to the other side. Well, I have to move this over here, right? XO. So if this increased by a factor of 9, right, this t squared increased by a factor of 9, that must mean that our initial position also increases by a factor of 9, because that keeps the ratio the same. And so you're thinking, wait a minute, so what do you mean by that? So to focus on that part, right, I want to focus on here. I'm going to carry this over here. So when our t was just t, we get something like this. I'm going to move this over here. We get xo is equal to t squared. Right, so that's the first scenario right here, when we just dropped it from a height of h and it was dropped to t. So I guess technically it should look like this. Negative h is equal to t squared. Okay, so that is our starting ratio. And so what the AP questions will look like is if we drop it so that it falls 3 times as long, so 3t, what will it look like? Or how high up will we drop it? So I'm going to erase this real quick so I could do this math again. So if we start off with 0 plus t squared, okay, I'm going to move this to the other side. I'm going to also change it to h. So negative h is equal to t squared. Here we put in the 3t, so we get 3t and all that is squared, so that gives us 9t squared is equal to negative h. Okay, but remember, this is a ratio. This is our starting ratio. So if this is our starting ratio, we must have the same ratio over here. So if we increase the right-hand side by a factor of 9, we have to increase the other side by a factor of 9. Because this here, we have a 1-to-1 ratio, right? If you were to imagine in front of this h, we have the number 1, and in front of this t, we have a number 1. Over here, we need to have this 1-to-1 ratio, and we have a 1-to-1 ratio because here we have a 9, and on the side, we also have a 9. Okay, so that's how they like to use the kinematic equations to ask you questions. And I am here to tell you that this anything squared, they love it. They love that squared value. It's one of their favorite things to do, because a lot of students, what they'll do, instead of plugging in like 3t squared and squaring both the 3 and the t, they'll just I don't know, they'll just square t, or they'll forget to square it all together. So they'll be like, oh, if I increase the time by a factor of 3t, that must mean that I have to drop it from a height of 3h, right? So they think like this is the correct ratio, but because that's squared, that's not the case. That is most definitely not the case. All right, so with the kinematic equations, sometimes you might come across a lab-based question. So I have a lot of things back there, so I'm just going to focus up on here. I'm going to highlight it so that you can see exactly what I'm talking about with these kinematic equations. All right, so with these kinematic equations, they like to ask like these lab-based questions. So when you're reading a lab-based question, so the lab-based questions, they will always start off with, a student wants to do a physics lab by doing blah, 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 right? And like whatever the scenario is. If you see a question that is a lab-based question, what it's actually asking is, can you identify the correct equation? So for example, if the lab is saying that you're trying to find the acceleration of a object, and you have like a stopwatch, right? So a stopwatch tells you the time, and you have like a speedometer or like a velocity meter. So a velocity meter or a speedometer, it tells you your velocities, right? And it's like, what are you trying to find? Like, what additional information do you need? And so in that scenario, right, it tells you that you have your time, you have your velocities, and so the only additional information you would need would be the acceleration. Okay, so take a look out for that. Another thing, like if I were to use this one, it'll be like, you are trying to figure out the acceleration of like an Apple machine. Okay, or you're trying to find the acceleration of a falling object. All right, so boom, right there. All right, so you're trying to find the acceleration of a falling object. You have a stopwatch, so stopwatch time. That's it. They don't tell you anything else. And you're like, what other additional information do you need if the system starts off at rest? Boom, starts off at rest. So we know that our initial velocity is 0. Okay, so if we take a look at this, we have the stopwatch, the time. You're looking for your acceleration. You have time. You have initial velocity of rest. What other information do you need? So in that sense, if we take a look at this kinematic equation, the only other thing that we need is the final position, right? And in order to find your final position, you can be like, you need a meter stick, or you need a measuring device that measures like displacement or position. And so usually a meter stick works well. And so that would be your answer choice, because that's the only other thing you need in your equation. So look out for that. For those lab-based questions, you are actually looking at your equations and seeing what variables they give you in your lab, and usually the question will be like, what are you trying to find, or what other tools will you need, and the tools link to the variable that you're trying to find. Okay, and so I said a couple of tools right there. One of the most common tools will be a stopwatch for time, a accelerometer for acceleration, and I call it a velocity meter, but it's like a speedometer, or like they use a term called photogate. So a photogate just tells you the velocity of the objects. Okay, so keep an eye out for that. All right, the one last thing that I want to show you is looking at position versus time graphs. I just want to recap that. So here we have a position versus time graph. All right, so if you have something that looks like, let's do this. If you have a position versus time graph that looks like this, and you're like, what happened? Right, so first off, you should be able to analyze this graph and create like a velocity time graph, or maybe even an acceleration time graph. Okay, so we will do that. Now, if this is a position versus time graph, and you're like, what happened, right? We can say that the object had a initial positive position. It went towards whatever they designated as position 0. Right? We don't know what that is, but it went towards that. And then it went back up, or I shouldn't say up, but it went back towards its initial starting position. Okay, you start, so like in terms of like, I don't know, like a track, right? So if we have a track here, and we say that right here, this is position 0. Okay, this person, it started right? Hello, this person on the track started there. They went towards 0, and then they went backwards to the original position. That's what this graph shows us. In terms of velocity versus time, same strategies, right? Break it up. We have part 1 and we have part 2. So we know that in between part 1 and 2, we have that part right there. Right there, your slope is pretty flat. So right there, that tells us that our velocity is 0. That must mean that this person stopped, right, at one point. And so here, if we take a look at the beginning, we have a very steep negative velocity. So we had a negative velocity, and it approached 0. So if I were to create a velocity time graph, we have a negative velocity. I'll do this in red. We have a negative velocity, and it approached 0, like that. Okay. And then in part 2, we start off with a 0 velocity. It looks like a smiley face, and it approaches a positive slope. So that means that we start off at 0, and we end up in the positive region. So this is our velocity time graph. Okay, and in order to come up with the acceleration time graph, remember the slope for a acceleration time graph tells us the slope for a velocity time graph tells us the slope. And here our slope is positive, so acceleration is positive. We don't know what that value is, but all we know is that it'll be somewhere above the x-axis. Okay, so we went from a position versus time graph to a velocity time graph to a acceleration time graph. All right, so you should be able to read these graphs and be able to go back and forth between those three. All right, hopefully you learned a thing or two. This is just my big overall recap of the kinematics unit. I wish you luck.